We go. All right, so it's a great pleasure to have Vijay Balasubramanian today, and he's going to tell us about knitting wormholes by entanglement in supergravity. Go ahead.
Hey, so it's very nice to see everybody, and thanks for the invitation to speak here. So Onkar asked me to speak about our recent paper on knitting wormholes by entanglement in supergravity, so I'm doing that. This is roughly speaking how to put this, my report on what I did in my summer vacation this year. So that's roughly speaking what this is. So this paper was written with Matt DeCross and Gabor Shadoshi. I think many of you know Gabor. He's now at CERN as a postdoc there. Matt is a graduate student with me who is graduating this year. He's done beautiful work, and if you have a position, you should definitely offer it to him. This is one small piece of his thesis that I'm talking about right here. Great, wonderful. So let's begin. So over the last decade, one of the hottest things in our field, or one of the things we've been most interested in, is this idea that the connected nature of space-time arises somehow from entanglement of the underlying quantum degrees of freedom. So where does this idea come from? Let me remind us that in its most basic form, this idea comes from the Ryo-Takayanagi formula and its HRT generalization. And how does that work? If this is a cross-section of AdS space, and over here I have some region and I wish to compute its entanglement entropy, we were instructed by Shinsei and Tadashi that we should find some minimal surface, some extremal surface in the bulk of AdS. That's supposed to be this red line, compute its area, and it tells us something about the entanglement in these degrees of freedom. And as we've understood, the degrees of freedom in this region encode the physics within this entanglement wedge. And there is evidence that as you increase and decrease that entanglement, the area of this red surface increases and decreases, suggesting that connectedness across the surface has something to do with the entanglement of the degrees of freedom on this side with the degrees of freedom on that side. Another piece of evidence for this kind of thinking, of course, has come from the eternal black hole, which we've known for now almost 2 decades, is related to a wormhole between two universes. So basically, we construct we take two CFDs, A and B, and we construct the thermally entangled state between A and B. So it's a pure state that's thermally entangled, a thermofield double state. And we know that this appears to be dual, just have a dual description as a wormhole going between these two regions. And indeed, again, in this case, as you increase and decrease the amount of entanglement, you can increase and decrease the area of the bifurcation surface, thereby, again, giving some evidence that this kind of entanglement is related to connectedness between these two regions. Another interesting piece of evidence from more recent work has to do with the whole islands and formula and the replica wormhole. So now this is an audience which contains many experts in the subject, and so not to repeat that work, which I'm sure many of you have heard about, I'll give you two examples of how this is supposed to work from some of our own work. So here's another example of a different sense in which entanglement is supposed to be related to wormholes. So suppose you had two disjoint universes, A, which has gravity, and B, which doesn't have gravity. And someone tells you A and B are in an entangled state. Please compute the entanglement entropy of this universe A, which didn't contain any gravity. So here, now I'm not talking about the black hole information paradox or anything like that. It's just some two-dimensional universe without gravity and some other universe with gravity. So now normally, if you wanted to do this using the replica trick, you would be instructed to take replicates of these two universes A and B, make many copies of them, and then you compute the Rényi entropies by running cuts between different copies of the universe A, and you compute the path integral, you compute the Rényi entropy, and then you take some limit. So now the recent idea, due to many authors, including several people who are in the audience, is that you should also, because B contains quantum gravity in it, you should allow wormholes that you wouldn't previously have considered between these gravitating universes. So not only should you sum over saddle points that look like this with the A's connected up to compute the Rényi entropy, but you should just sort of egregiously add in, just because you can, topologies which involve wormholes between these gravitating universes. And it appears that if you do this, the replica method for calculating the entanglement entropy seems to require the inclusion of such replica wormholes, Euclidean wormholes between these gravitating universes in order to correctly reproduce the entanglement entropy in a way that respects unitarity. So this was in the case of two disjoint two-dimensional universes. You can also do this in, for example, 3D gravity. So here's another example where you imagine following the kind of style of the replica work done, on the West Coast in Stanford. So you imagine some BTZ black hole where you have behind the horizon, you imagine that the microstates are on some end of the world brane over there. And then you imagine doing holography for that brane. Then if you try to compute the entanglement entropy associated with the entanglement of these microstates with some radiation that's off somewhere else, you're led to consider the holographic dual of this end of the world brane, and you get some picture like this in Euclidean space where you have this is the original black hole, this is the this has to do with the geometry that's dual to this wormhole, and then you once again consider trying to do the Renyi approach. You try to compute replicates and you compute the entanglement entropy, and this is supposed to be just a schematic. You again find an exchange between saddle points where you wind up including, in this case, multi-boundary wormholes between different copies of the replicated gravitating universe, and this again seems to rescue unitarity in a calculation of entanglement entropy. So this is a different kind of relationship between entanglement and wormholes. And so now we've seen three examples of this kind of relationship between entanglement, connectedness, and wormholes. And the three examples are: one, the RT formula, which sort of is a direct relationship in entanglement, the size of bulk surfaces in AdS-CFT. The second one was the special example of the thermofield double on two asymptotic universes that are connected. And the third example is a slightly different feeling example where you have, you're doing the Euclidean calculation. It's not a Lorentzian wormhole, it's a Euclidean calculation, but nevertheless, it does seem to be the case that whenever you have entanglement, you need to somehow include these kinds of, connected geometries of some kind, which we might call wormholes. So I think it's fair to say from all of that, at least in my speaking for myself, I don't fully understand a couple of things. So one thing I don't really understand is how much entanglement do you really need in order to have a large wormhole? And is there something special about the patterns of entanglement that become geometrized in that way? So for example, we know that in gravity, it's very difficult to realize GHZ style entanglement between three parties, whereas W style entanglement is easier to realize. So that makes me wonder, well, what kinds of patterns of entanglement can be are related to connectedness or not related to connectedness and so on. So these are all questions that would be nice to sort out. So as related to this present talk, we thought that it would be interesting, it would be nice if we could really do the following thing. So in order to elucidate these questions about what kinds of entanglement, does entanglement always lead to connectedness, it would be nice if you could do something like this. First, I'm going to take some universe with some asymptotic region, and I'd like to construct some sort of state with probably suitably large entanglement between the quantum degrees of freedom that are associated to two local regions A and B. So here we're thinking that we're talking about an already connected spacetime with one asymptotic region. And now I've got two regions of it, and I'm going to entangle them. So if I really believe that entanglement is somehow related to connectedness, then, well, there's a new connectedness. It's not the connectedness that was already there. So we should imagine that this entanglement that I put in by hand into the state should lead to a wormhole between A and B. And by wormhole between A and B, I don't want to mean a small quantum wormhole. I mean a wormhole. I mean something that gives me an alternative geodesic path between these regions. They were already connected, so there was some path between them. But now I imagine that I have an alternative geodesic path. So really, it would be so nice if this alternative path could be used to do all the stuff you'd like to do in science fiction. So that the Klingon ships blocking you from going from A to B, and you'd like to go through this alternative path to get around them, or do whatever it is that you get in 2001: A Space Odyssey, all the stuff that wormholes are supposed to do. That's what you'd really like to do. But we'll settle for something less wonderful. We'll settle for just having that wormhole be traversable, at least, so that you can get from A to B. It's not just a space-like path, but you can get from A to B. It would be really nice if there was an algorithm where anytime you make the suitably designed large entanglement in two regions, you can find such a wormhole. And, and while we have all really enjoyed all the progress we've made using low-dimensional toy models, it would be really great if we could start doing this kind of thing in complete quantum theories of gravity, like string theory, so we could embed everything we're learning at the current time in the whole framework of D-branes and, whatever, all the stuff we learned about black holes prior to the exciting recent developments. So we're going to
could I ask a super naive question?
Yep.
Okay, great. This is really just for context for me. I expect maybe lots of the experts know this already. I mean, there were old theorems in general relativity saying that if you had blah, blah kind of space, and then you wanted to imagine a new solution of the Einstein equations that still had blah, blah, but added a wormhole between this and that, you would have to violate some cherished condition on energy or causality, blah, blah. You know, some of the standard lists.
We're gonna, to get a traversable wormhole, you're going to need to violate some condition. We're going to violate the average null energy condition.
Okay, and you're going to say that in whatever setup you have, that's fine and valid, and it comes from some reasonable source.
This is like the Gauss-Jafferis wall protocol, except that what we're going to find out is that it appears naturally. So we're going to take some field theory. We're going to do something to basically Higgs it. We're going to try to argue that if you RG flow it, it generates naturally the operator. I actually don't know the sign, if it generates it with the right sign. But anyway, we're going to argue that it generates operators in the form that you might want to use to produce this.
Okay, got it. Thank you.
That's going to be the idea. But that's an excellent question, obviously. Anyway, so this is what we're going to try to do today. So here's our approach. So in case I don't get to the end of the talk, I'm going to sort of tell you the bottom line from the beginning. So we're going to consider standard AdS-5 CFT4, right? So n equals 4 super Yang-Mills of the SUN gauge group. And we're going to suppose that we're going to take that theory, which is dual in the vacuum, to AdS-5. Then we're going to Higgs it. So if we Higgs it, as you know, the Higgsed theory looks, if you take the dual of it, like some sort of two-center solution. That is to say, as you go out far away, it looks like the single SU, AdS space, but somehow as you go into the interior, you should somehow find the two factors of the Higgsed SUN. So you should find one throat, which is one of the Higgs factors, and the other throat, that is the other Higgs factor. So at the moment, well, okay, so actually here I'm talking the language of D-branes in flat space. So really, if I want to talk about an AdS-CFT, I need to take some kind of decoupling limit. So I take alpha prime to 0, while at the same time bringing the two centers close enough together in the appropriate scaling way. We'll do that. And at the end of the day, you'll get a solution of this kind, which is asymptotically AdS-5, but has two smaller AdS throats. Now, what we want to do is to recognize that in the infrared, you've got two SUN gauge theories. So I should be able to entangle them. By scaling the ends in the right way, there should be lots and lots of, order n squared degrees of freedom in the infrared. And that should be plenty enough to entangle in a more or less thermal way in order to get something that ought to look like a black hole, like an eternal black hole in infrared. In other words, we should somehow be able to take this throat, the two throats in the global AdS-5, and we should be able to take, basically the two-sided black branes, what looks like the eternal black brane, and kind of basically stick it in. And that should give us a geometry, if we believe AdS-CFT duality and the general, states in field theory must be dual to states in gravity kind of thing, then we should be able to do this. Okay, so that's the idea. It's going to turn out that there is a wrinkle or a subtlety, and that you can only do this while preserving flux conservation and orientability and stuff like that. If you do something slightly peculiar with the topology, you're going to need to take this black brane and do various inversions and stick things back in. So it's really more like gluing in a Klein bottle. I will discuss that in more detail, but barring that, that's the construction. And then I'm going to argue that the thing is marginally traversable, and then you can add some operator to it to make it traversable. That's going to be the idea. Okay, so to summarize, what is the outline of the talk? So, the overall solution we're going to construct is going to look like this: an asymptotically AdS-5 geometry with two throats, which have we'll call it poetically a Klein bottle-like thing stuck underneath that will locally look like the black brane geometry. So we're going to go in 6 steps. We're going to first discuss in detail why SUN super Yang-Mills theory predicts a wormhole in a single universe. Then we're going to construct the wormhole geometry in supergravity by just going through these various regions and sort of figuring out what they should look like. I'm going to spend a little bit of time discussing the global structure and the flux conservation, because that's the trickiest part of the construction. Then we'll discuss the fact that actually this had better be unstable. And so really this will be an unstable wormhole, and what you really want to guarantee is that the instability has a sufficiently long time scale. So we'll do that. Then we'll discuss traversability of this wormhole. And then finally, I will argue to you that the exact same construction gives you for free construction of a double wormhole between two universes. So that's the plan. Any questions so far?
So is this going to involve...
Go ahead, Eva.
I was just asking, is this going to involve Casimir energy?
Oh, no, I'm not going to use any Casimir energies.
Okay.
Vijay, my question is, are you going to talk about what this means in the boundary gauge theory?
Yes, that's what I'll start with.
Okay.
because that's where we may have some purchase for thinking about various things about this later on. So, this is the first work in this kind of thing. And yeah, you'll see. Yeah, I will. Yes. So here we go. There's a lot more to be done in the boundary gauge theory, actually, but I'll tell you what I can. Somebody had one more question?
Yeah, I have a question. So can you also say which directions are compact and which are extended?
Sure. So I'm going to take this to be the Yang-Mills theory on the plane. So basically, everything is an infinite black brane. So what's going to happen is that there's going to be asymptotically, the geometry is going to be, R31 for the plane on which the Yang-Mills theory lives, and there's going to be an S5. Then as you go into the interior, that sort of product structure will kind of break down, and it'll be a full 10-dimensional geometry. It'll do what it has to do, and then come back out. Does that answer your question?
Yes, thanks.
Okay. All right. So let's start with the Yang-Mills theory. So let me remind you. So here's the Lagrangian of the n=4 super Yang-Mills theory. The only reason I wrote it down is I was marveling over the fact that Keynote now allows you to type these equations in, so I did for fun. Anyway, so here's the Lagrangian of SUN super Yang-Mills theory. So we're going to consider an SU2n gauge theory. This thing has 16 supercharges and is the low energy theory of D3 branes. So as you know, it contains a gauge field. It contains a bunch of adjoint fermions. Those are these lambdas. And it contains 6 adjoint scalars. Those are the phi i's over there. So if you look at this Lagrangian, it's got commutator everything in the Lagrangian, the gauge fields and the fermions and the other scalars. They all have commutator terms with these scalars. So that's one statement. The second statement is that this theory in the vacuum, because of the supersymmetry, has moduli space, which is to say that you can take the scalar fields and give them vevs, and you'll still be on the vacuum manifold, right? So the way you Higgs this theory is you give let's say you give an adjoint scalar a vev, and you interpret that in D-brane language as separating the branes into 2 stacks of D-branes. So that's what we're going to do to generate, from our SU2n theory, 2 low-energy SUN theories. So how do we do this? Well, let's take one of the scalars phi1. So that means we're moving the stack of 2n D-branes apart along the direction 1. And we split that gauge field, that scalar field, into psi plus phi1, where phi1 is going to be the fluctuation, and psi, the fixed background, takes the following form. So here, it's going to be a matrix that basically has 2 eigenvalues, each repeated n times. So that necessarily, because of the commutator terms here, is going to wind up splitting the gauge field into 2 like pieces. So it's going to be an SUN cross SUN kind of thing. And I have, knowing how things are going to work out in the equations later, I have cleverly, parametrized these expectation values in terms of some scale lambda times a root n over 1 over 2 pi alpha prime, because we're going to play games with the n and the alpha prime later. So if you set up such a vev for, let's say, the scalar field phi1, you're going to find that the off-diagonal pieces of all the gauge fields, the scalars, and the fermions acquire a mass of lambda root, big lambda here is the parameter for the vev. Little lambda here is the Toft coupling, g squared Yang-Mills n. So it's big lambda square root of little lambda divided by 2 pi alpha prime. Great. So that's going to be the mass of the off-diagonal fields. So we're now going to consider an IR. We're going to now consider a state in this theory, and we're going to take. Let's say that I over here are sort of effective IR states in the light fields in each SUN. So let's consider something that looks like a thermofield double state. So I'm going to take I in the left SUN and I in the right SUN, and I'm going to multiply them by e to the minus beta EI over 2, and I'm going to do the sum up to some cutoff in the energies where the cutoff is set by the Higgs scale. So this is supposed to only excite those states that are below the Higgs scale. So it's only the light fields that are being excited. Of course, this simple way of doing that is to pick a temperature low enough, well below this Higgs scale, so that you're only going to sort of tickle the fields within these 2 light factors. So how would you interpret this state if you were just doing standard AdS-CFTology? Well, you would say in the UV, this is SU2n Yang-Mills theory, so I should find a AdS5 cross S5 of the standard variety. In the IR, I would say, well, there are 2 SUN factors, so I should find 2 throats, one of SUN, the other one of the other SUN. Well, but also because the states in those two throats are entangled with something else. If I traced out the other factor, it should be that the theory looks thermal within each of the throats. So if it looks thermal, it should look more or less like an AdS-Schwarzschild black brane. But I know that there's no place else, there's no other universe to go. There's only one theory. So it's got to be that black brane goes from one of these throats to the other one of the throats. In other words, there should be here a wormhole between two AdS throats that come back together asymptotic. Fine.
Vijay, can I ask another question?
Definitely.
Okay, I at least naively, I would have thought if you tried to build a thermal state on the Coulomb branch.
Yeah.
Oh, I see. You're non-compact. I was worried that there'd be a thermal mass and they would just roll back together.
They will. So let's discuss the potential next. So I've made it non-compact, so it won't roll that easily. But strictly speaking, you could cut the thing off somewhere, or you could put it on a torus. There will be an instability. So let's discuss that. Right. So the next thing, of course, is what Chaman said. So obviously, if you heat this thing up, there's going to be some kind of effective potential. So we already said that reducing the thermofield double state that we just made on either SUN is going to give something that's thermal to an excellent approximation. And so long as the temperature is much smaller than the Higgs scale, so beta inverse is less than lambda square root of lambda over 2 pi alpha prime. But as Shamit said, the finite temperature breaks supersymmetry, which will generate a potential on the scale of moduli space. If you make the thing all non-compact, you can sort of you can try to make this thing very slow. But let's suppose that it's on a large torus or something. And anyway, so it'll generate a potential, and this will be minimized at the origin. So another way of saying this is that in gravity terms, if you take two stacks of D branes and heat them up, their mass will exceed their charge, so they're going to attract. So that's what will happen. So what is the effective potential controlled by? So strictly speaking, we should be calculating the effective potential at strong coupling, which ain't going to happen. So what we should do is we should first ask, what is the parameter that controls it? And it's clearly going to be controlled by the ratio of the thermal and the Higgs scale. So here I've taken the Higgs scale. Well, I've taken the thermal scale, which is 1 over beta, and then divided by the Higgs scale. So that's why you have a 2 pi alpha prime over lambda root lambda. And if you can rewrite it like this, you can rewrite it in terms of a parameter R naught, which is a certain combination of the alpha prime and root lambda, which is going to turn out to be the horizon radius of the system in the gravity description, divided by lambda, big lambda, which is the separation between the D branes in the D brane language, times 1 over the Toft coupling. So this combination, roughly speaking, is in the gravity side going to control how thermal the system is, the horizon radius, as compared to the separation between the two throats. So you can see that that's going to control how long it's going to take for the stuff to fall back together. So that makes some sense. But there is here a 1 over the Toft coupling. So we should remember that we shouldn't try to match this epsilon exactly on the gravity side, because whatever the gravity side is a resummation to all orders or something of the strongly coupled version of this theory. So very often we find, of course, that when we do that, what happens is that you take a parameter like this and it'll get multiplied by some function of the Toft coupling, and we will see that that is what will happen when we do the calculation of the instability timescale on gravity. It'll be controlled by parameter that looks like this. Well, f of lambda will actually just be lambda, so it seems to cancel out the little lambda, the Toft coupling exactly. So that's going to be the setup. Okay, so that's all I'm going to say about the field theory right now, because I do want to talk about the solution.
So Vijay, just a small comment. I mean, if you took flat like Poincare slices until you heat it up. If you did the negatively curved slices, then the fiducial potential is actually outward. So if you then heat that up, you could probably balance the two or tune the two against each other to even worry less about this issue.
Oh, I hadn't actually realized that. That's kind of cool.
Yeah, I mean, you're used to the fact that when you're on the sphere, there's just in vacuum, there's a potential inward, flat, none until you heat it up. And then it goes the other way when you have the negative curvature slices.
Okay, that's interesting. I had not realized that. And that's something that would be, when we get to the end, I would love to revisit that again and maybe chat also offline, because that's interesting. Because I've been wondering what else can you do with this? And you'd like a system which you can control better even than this. And so I'd love to chat about that, actually. I hadn't realized that.
Sure, thanks. No need to stop the flow now.
Okay, then I'll keep going to the next thing. Fine. So now knowing something about Yang-Mills predicts the solution exists, and Yang-Mills predicts that there is a parameter like this that controls the instability, we're going to try to construct the solution in gravity. Fine. So, well, what's the gravity theory in question? It's the n=8 type 2b supergravity, which, as you know, has an action that looks like this. There's a there's a Ricci scalar, there's a dilaton floating around, and there's a 5-form gauge field that will go along with the game. And like all good people, we will ignore any fermions and don't need them. Great. So I'm going to make an ansatz here. The ansatz is going to be that the dilaton is constant, and we also have to impose self-duality of the 5-form as a constraint. So if you do those two things, impose constant dilaton and impose self-duality of the 5-form, you can go ahead and work out the equations of motion, and they're kind of nice and simple. You find that the Ricci tensor, r mu nu, is equal to the square of the 5-form, and you get some divergence condition on the 5-form being 0. Right, source-free condition. Great. So how are we going to construct the solution? So we're going to construct the solution in perturbation theory. Solving these equations exactly for the finite temperature case is not, well, we don't know how to do it. So we're going to do this perturbatively. Okay. So in any perturbation theory, what you do is you start off with a background solution that you understand well and is nice and stable, and then you add perturbative corrections and solve the equations of motion. So indeed, we're going to take some background solutions for these, these various regions 1 through 5, and we're going to take that background solution, add a perturbation to it, and we're going to do that same thing for the 5-form. In the background solution, we're going to add a perturbation to it, and then we're going to work out what the perturbation equations say to whatever order we need to get the perturbations to in order to be able to analyze things like the instability of the solution and match things consistently across the various regions. Great. So I'm going to start out with the asymptotic regions because they're easiest. So that's this part here, which is basically the asymptotic AdS-5 plus the 2 throats going in. So we're going to do exactly what we said we did to get the n=4 angles in the first place. So this is all for people of a certain age. If you like, this is all completely second nature, but I'm going to repeat this for, I suppose, the younger students who probably haven't seen these things. So we're going to start with an asymptotically flat space with 2 stacks of D3 branes displaced in one transverse direction. So the solution looks like this, where these are the x's are the directions parallel to the branes, and the ri's are the directions, the direction 6 directions transverse to the D3 branes. Now, famously, if you're talking about extremal BPS branes, there is a thing called the harmonic function rule, where you can write down the full solution, the superposed solution for a whole bunch of different branes separated from each other by taking this h and writing it as 1 plus harmonic functions associated with the centers of each of the branes. So here we've placed some fraction, some number of the branes at the origin. So you have L to the 4th over R to the 4th. R to the 4th is, this is the correct harmonic power for the number of transverse dimensions that a D3 brane has. And then we've put the other stack of branes at a location lambda. So that's lambda in the R1 direction and 0 everywhere else. That's just like the Higgs value we were considering earlier. And you write down L to the 4th over R plus lambda, magnitude to the 4th, and that'll give you the solution. So well, actually here, yes, okay. So then there's and as usual, the AdS scale to the 4th is equal to 4 pi g string times n. N is the flux in the solution, is the total flux of the 5-form. That's also the number of d branes in the solution times alpha prime squared. Okay. So now, if we take the standard way from this asymptotic flat solution, I remind you to get the AdS solution out of this is you take the decoupling limit, which means you tend alpha prime to 0, and here the parameters we're going to keep fixed, or we're going to keep lambda, the separation between these 2 stacks of branes, fixed in alpha prime units, and we're going to at the same time focus in closer and closer to the solution by looking at by keeping fixed Ri over alpha prime. And if you do this in the time-honored way, essentially what happens in the solution is that you lose the 1 in the harmonic function. Basically the rest of it comes in. And if you take this and you stick it in, that is supposed to be the exact solution associated with an asymptotic AdS-5 that then develops 2 throats. We can check that if you take the asymptotic limit, that Ri is much bigger than lambda, so you're very far away. So in other words, you go far away from the separation of these 2 throats, you will recover the standard metric of asymptotically AdS-5 geometry. So that's good. And then it's useful to actually visualize what this geometry is doing. So normally when you talk about AdS-5 plus S5, you have the AdS-5, you have a factored sphere. So in some sense, what's going on is that you have a stack of D3 branes sort of separated out on one, let's say the north pole of the sphere. You've got another stack on the south pole of the sphere. Each of them is making their own little throat. So as you come in, if you like, in the north pole of the S5, there's a throat going in, and the south pole of the S5, there's another throat going in. They're separated by a certain kind of distance. It's sort of that's the kind of thing. That's a little bit misleading because I talked about that as though there is a sphere S5, and then you can go to the north pole and the south pole. Strictly speaking, as you come towards the interior, the geometry is not factorized, and that's actually going to be important for us as we get further along in the talk. But anyway, so that's roughly speaking the setting that we're talking about. So now, yeah.
So what is the plus minus sign?
Yeah, that's a typo. You can pick plus if you like, or you can pick
Okay.
really matter. But thanks for the question. Okay, so then now we have the background solution in the asymptotic region. So now let's talk about the background solution in this interior region. So this black brane solution. So once again, we're going to do the same thing. So the solution here in this interior region should be the two-sided black brane with corrections in the end from the presence of a second throat. In other words, if I had the two-sided black brane, this thing would be asymptotically AdS on both sides, but clearly that needs to be adjusted in some way in order to splice onto the fact that if I go out here, it's not just asymptotically AdS, it changes over, and then eventually there's the effect of the second throat, and they all add up and make an even bigger AdS. So that has to somehow happen. But let's just start with getting the background, and then we'll correct it. So the standard asymptotically flat black brane geometry has the following form. Again, you have these harmonic functions, h of r, as in the extremal solution. But now, because it's non-extremal, there's this function f of r, which looks like 1 minus r naught to the fourth of r to the fourth. R naught is going to be the horizon. You can see that because if you set r equals r naught, this f of r goes to 0. So then this coefficient becomes 0. So that's the horizon. And then there is some phi form field that goes with this. Once again, we can extract the piece we need by taking the decoupling limit. So we'll send alpha prime to 0, keeping various things fixed. In particular, we keep the horizon scale fixed relative to alpha prime. We keep the transverse coordinates fixed relative to alpha prime. So we come closer and closer and closer as we send alpha prime to 0. You have to rescale the AdS scale and the various parameters. So if you do this, you get a solution of exactly the same form. But as usual, in these kinds of scaling limits, you lose the 1 in the harmonic function. So that makes this thing sort of asymptotically AdS. And some things happen to the phi form where this overall factor sort of goes away. Anyway, so that's the standard sort of local form of the black brane solution in AdS5. And we've extracted them both using some scaling limit. Okay, we now have our background solution. We have a two-center solution in the regions 4 and 5. And we have the black brane solution region 1. If you compared them, if you compared the two-center solution deep in the interior and the asymptotic solution of the black brane, of course, they don't exactly match. So what you need is you need to somehow find a way of sewing these together. And the way we're going to sew these together is we're going to add corrections in these regions 1, 2, and 3 in such a manner that the geometry smoothly goes from one thing to the other and continues to solve the equations of motion up to whatever order in perturbation theory we have the strength to work in. Okay, so that is a technical calculation. And, if you like the technical, the most space in our paper is spent on doing that matching and everything like that. So that would be tedious to discuss on a talk. So I'm just going to tell you what happens and how it happens. And then we'll go on to the conceptual issue of, this funny thing about the global flux conservation of the topology. So this is the way we go about doing the matching. And you're going to have to believe me that we did the calculation correctly. So first, if you look at regions 2 and 3, they're quite far from the horizon over there, and they're also very deep into a single throat. So if I look here, this region here is deep into this throat. So, well, this other throat can't matter too much, and it's also very far from the horizon, so this horizon can't quite matter too much. So really the solution here is going to be more or less like the vacuum AdS5 solution with, the smaller cosmological constant than the asymptotic region. So that's going to be the basic solution. So the effects of the second throat and the effects of this horizon can then, in leading order perturbation theory, you can linearize this. You'll get some linear correction. And because you're working in the linearized equations of motion, you should be able to just add those two linear corrections together, and that will give you a solution. So to leading order, that's going to be the solution. So then the next thing you have to do is, well, that's not quite good enough to actually match all the fluxes and match everything together and get the solution. The next thing you wind up having to recognize is that if you look at this region 1, then the presence of this other throat winds up acting in the equations like a sort of monopole source, a source that preserves the symmetries. The SO6 times SO3, symmetry of the solution is preserved by the effects of whatever source over here is affecting the geometry here. So then using that, you can solve the equations of motion and get a correction in this region that allows it to splice onto the regions 2 and 3, and this correction also decays away as you go towards the horizon. Then you've got to correct the solution the other way. You have to come here and then ask how to correct the solution here so that it splices onto the other asymptotic region and into this region 1. And it turns out now to get that to work correctly, you have to recognize that this throat breaks the spherical symmetry around this one. In fact, remember I told you that the two throats are sort of at the north and south pole, if you like, of a sphere in some sense. So that's going to break that symmetry. So there's a dipole correction you've got to put in order to be able to splice correctly. And that takes some work to work out. But, you know, at least logically, it's not a conundrum. You know what you need to do. So you work out that solution, you add it in. And I'm not writing it down because it's complicated to write down. But at the end of the day, you have a full solution, a perturbative solution up to this dipole order that interpolates everywhere in this space. And the one key thing is that the full geometry does not factorize into AdS times a sphere and is some fully 10-dimensional solution. It factorizes, of course, in special limits up there near asymptopia, near the asymptotic region, and deep in here it factorizes, but overall it does not factorize.
Vijay, I'm a little confused why you have an exact linearized solution instead of one where there's a small tadpole because of this attraction.
Because the attraction comes in a couple of orders down.
Oh, I'm sorry. Okay, and that's obvious just by doing some counting in lambda or something?
That's doing some counting, and we're going to evaluate that attraction by doing a probe brane calculation. And it'll turn out that the attraction force is suppressed to certain numbers of powers in the perturbation.
Okay, would that have been obvious going in, or were you lucky, or?
The answer to both parts of that question is yes. Because we tried to make some estimates using the Yang-Mills theory, so we sort of expected it. Then it turned out that the estimate was not quite right for various reasons. So then there was a certain amount of answer analysis that we found the answer. Then so it was the usual situation. We expected it, but then we got lucky.
Super, thank you.
Okay.
Also, the perturbing parameter is this epsilon that you had before, or the temperature, so it's at small temperature?
Yes, this is all done at small temperature. So the relevant thing that determines whether the temperature is big or small is a comparison with the separation scale of these branes. That'll become apparent when I do the instability analysis.
Okay, thank you.
Yeah.
And Vijay, is this intended to be a solution for all time, or is the picture you're drawing a picture of some solution on a surface of time symmetry?
Yes.
And that's the spatial geometry?
The spatial geometry at some moment in time, you should think about this.
So I should view this as some kind of initial condition for some.
Yes. So you should view this in a sort of adiabatic kind of sense. So you can have, as we'll see, you have parametric control of the time scale of the instability. Because that's just, you can scale everything you scale the AdS scale to be enormous. That's just making n really big. Then you make the separation scale of these two throats to be really big, but much smaller than the AdS scale, or not scaling as fast as n. Let's put it like that, right? You make it big.
Kind of thing I'm wondering about is so you're sort of trying to correct the solutions in region 2 in order to sort of match onto the geometry further up and further down. And it seems to me like that's just going to create some kind of an initial condition where there's a lump of stuff in that region. And that lump of stuff is either going to be radiated out to infinity or it's going to fall into the throat.
So I'm not going to have a good conceptual response to this because I don't understand it in a conceptual way, but I can tell you that order by order up to, we'll see which order that is in epsilon, up to order epsilon squared or epsilon cubed, you can do this in a source-free way. So there's no sources there. And you're solving the standard vacuum equations with the AdS5 plus S5. I think you're asking me, why isn't there a lump there?
Yeah, but the lump is a lump of geometry, right? Plus
sure,
5.
Well, Well, but you're wondering why isn't there some stress tensor there?
I'm wondering why there isn't a bunch of supergravity radiation there. Yes.
Well, I think eventually there will be. I think the answer to that must be similar to the answer that I was giving to Shamit's question, which is that you can control the time scale of the instability. So eventually this thing will start moving, and when it starts moving, it'll radiate. But it's going to be quasi-static to, I don't know, power epsilon to the fifth or something like that. And as a result, it's sort of kind of stable for a while, and while it's stable, it's not radiating. Does that answer your question?
I think so.
You're probably about to talk about flux, but somewhere there must be at least a source for this, like 2n units of flux.
Oh yeah, we'll see that. Let's see that. That's exactly what I want to talk about next. Because where is the, what's happening to the flux? Because you got to sort of move it around from here to here. Where is that coming from? Let's talk about that. Yeah, that's a very good question too. Yeah.
All right, before you go on from this page, can I ask a sort of related question? I mean, suppose, did any of this really depend on, I know you wanted the gauge theory side, but still at the end of the day, it was two entangled low energy warped throats, right?
Yeah.
Suppose you had a compactification in a much more generic situation with many such warped throats that happen to, for whatever reason, be in an entangled state. Do these methods allow you to piecewise kind of form a solution similarly? In
Yes.
other words,
yes. So one of the things that I would love to think about, but I don't quite know what the right question to ask is once you have the solution, you don't have to start with the n equals 4 Yang-Mills or anything. These are, in the end, we're solving some bulk local equations, and we just have a way of splicing everything together and so on. So, you could fantasize, like you remember how, Willie and Tom Banks used to talk about dense gases of black holes. You could imagine dense gases of wormholes. I don't know quite what to do with these things or what they would be useful for, but you could indeed imagine a tangle of these things, because locally you could try to build those solutions. So I don't know what the consequences of that would be or what they would mean, but they could in principle exist. In the context of the n equals 4 super Yang-Mills, you could think about that also in the sense that you could, of course, Higgs the thing down to many factors and entangle them in some crazy quilt way, right? Who's to stop you, right? And you could ask the question whether you could, that would, quote, predict the existence of the corresponding solution, which would, be unstable and everything will fall together. But can you make those things? So in principle, the answer is yes.
yeah. So in other words, a bunch of hidden sectors could be secretly joined together for whatever that's
for example.
worth, for whatever that's worth, right? Okay, thanks.
Well, no, that's worth something. That's worth something. Actually, I've been thinking about something with Jonathan Heckman and some LHC experimentalist about something like that. But not precisely that. But that's, I think, a very good question. That's a thing you might think to do with this kind of stuff.
Okay, great. Thanks.
Okay. So, So next, let me come to the subtlety, which is related to what Andreas talked about. So here's a puzzle that if I said I have a solution, and you might say, well, hey, wait a minute. Both of these throats are supposed to have n units of 5-form flux, quote unquote, pointing towards infinity. It's a little complicated what you mean by pointing towards, because this is, a 5-form flux, it's self-dual, and there's the S5, and there's radial direction. But anyway, there's sort of n units of 5-form flux coming from each throat, and there should be 2n units of flux asymptotically. But then you could say, how can this be if there are no sources inside the wormhole? Because you would think the flux would sort of thread through the wormhole and close outside, giving 0 net flux. So it's useful to think about this using an analogy, right? So suppose you had a magnetic field in 2 dimensions. You know that the circuit integral must be conserved if there are no sources for the curl. So if you had a 2-dimensional wormhole like this plot, right? Here's this 2-dimensional space, you run a wormhole around here, and let's suppose you ran a magnetic field around it. Then it's pretty clear that the magnetic field would have to go around like that, and by continuity come around pointing the other way. So if I had a circuit integral around both of the bases of this wormhole, clearly the answer would be 0. So you'd think that to avoid this, you would need to introduce a source in the middle. But there's another thing you could have done. You could have imagined that the wormhole instead was sort of inverted like this, right? It was glued with a twist, so that in effect it was non-orientable. It was like a Klein bottle. And then you could fix it so that there'd be a net flux, but you have to play games with the geometry, right? So you didn't add a source, but you have to play games with the geometry in order to glue things in a funny way. So we're going to have to do the fancier analog of that. So this is a little bit complicated, so I'm going to go through step by step, or I'm going to try to go through step by step. So here, I'm trying to draw a picture of, here is the Penrose diagram, if you like, of the wormhole. So here's the left asymptotic region, the right asymptotic region, and that stuff. This is the usual wormhole picture. And here's the first throat that's supposed to be splicing in to the left part here. And here is the right throat that's supposed to be splicing in to the right part here. Okay, so we are going to try to find some sort of twisted gluing of the wormhole that conserves the flux and preserves continuity, and overall is going to use the full 10 dimensions to preserve orientability of the whole thing. So the first thing to note is the left and right throats share a time coordinate. There's a global time that's flowing down from infinity. And there's also 3 globally defined spatial coordinates with the same orientation outside the throat. That's because that's coming in from infinity, and they're just going along for the ride along the parallel direction of the D3 branes. So we have those in our hands. The next thing to note is that the radial and the angular coordinates of the throats do not actually coincide, because this is what I was saying earlier, that the geometry is actually fibered in some complicated way near each throat. And so the 5 spheres in the 2 throats are actually centered around different points. So what you call the radial direction and the angular direction are different between those two throats. So that's useful to keep in mind. The next thing to note, and these are all just sort of facts that we're assembling before we actually do the construction, is that if you just write down the solution, both the electric and the magnetic parts of the 5-form field are going to be oriented the same way in the ambient space, and thus both in throat 1 and in throat 2, they're going to have the same local expression in terms of the coordinate differentials, which I've chosen to draw in these different ways here, because the theta 1 here is not the same as the theta 1 there. It's a different theta that's pointing in. But that's what the solution is going to look like. And that's what we've got to splice together through this wormhole. So how do we do this? So first, let's just pick some coordinates. So I'm going to pick Schwarzschild coordinates to work in for the wormhole. And I'm going to pick the Schwarzschild coordinates in the left wedge of this wormhole to match the left throat, so that the radial direction lines up, the t lines up, and the theta lines up. I can do that, so I'm going to do that. But if I do this, the Schwarzschild coordinate in this right wedge points oppositely from the right throat. So because we want time to keep running the same way, we will glue the right wedge of the right throat with a t inversion here, so that the time points in the same way in both directions. And now we're going to use continuity. So the way to use continuity is the next thing to talk about.
Sorry, question?
Yeah.
So if you do this in the wormhole geometry, would you get instability? Because you can have excitation of both positive energy from in the left and right side, right? In the usual case, we have at the wormhole time going upwards in the 2 sides, so that it's stable. But if you have one going up and one going down, I think that geometry would not be stable.
No, this is going to be stable. There's a single global time that you're running through everything. This is simply a coordinate statement of if I write Schwarzschild coordinates here and Schwarzschild coordinates here, I'm going to flip the t to match it up here and line it up.
Not sure, because locally at the bifurcation center you can have a global time, and then you have that is positive definite, but then when you express a Hamiltonian in the left and right, if the time are in the opposite direction, then you can have both of them will be indefinite, right? Because you can have positive energy in the.
If you prefer, you can repeat this construction in some sort of global time coordinate of the wormhole. I'm just trying to describe this in Schwarzschild coordinates so that it's convenient to do so in the coordinate thing. But you can describe this in Kruskal coordinates of the wormhole if you like.
Well, I mean, just in the Schwarzschild coordinates, if on the right, if time going up is the Hamiltonian is bounded from below, then you change the sign, then it becomes unbounded from below, right? I'm simply saying the following.
So I'm not sure actually that I'm entirely following, to be honest. So what we want to do is we want to put these things, the t that you've chosen here is a coordinate direction that you've chosen. So time is running this way. So we want to put it all together so the time runs in the same way. everywhere, right?
Okay.
Can we come back to this at the end of the talk?
Yeah, sorry. Yeah.
I think I may not be understanding the question entirely, actually.
I have sort of the same concern as Shinbin. Maybe we could, maybe I'll ask something different. Maybe it's a slightly different question. I'm not sure.
Okay.
Could you use your construction to make a wormhole connecting two copies of the original field theory that was time independent under forwards time evolution on the two sides? Are you claiming that? Sorry, I asked my question poorly, so let me try to do it better. If we take the ordinary two-sided black hole, then it's independent of a time translation that goes up on one side and down on the other.
Yes.
Are you saying that by gluing the wormhole in this way, you can make a solution that's independent of a time translation that goes upwards on both sides? Because I think you cannot do that. So
yeah. So I don't think that that's what I said.
Okay, but it looks like, okay, sorry, maybe I'm not following your construction very well.
Yeah.
It's not, you can't, you can't just flip time on one side and glue it together. Yeah.
Right. So I think I'm just trying to make a coordinate statement as to which way we need to have a globally oriented time that's going to go through the whole thing. So I'm trying to orient the times the same way to put them together.
Right, I guess
Okay, so let me propose that I keep going through this, but we come back to this point at the end because this is important.
Okay, that sounds fine.
Okay, let's come back to this in a minute. So I'm going to keep thinking about it, unfortunately. So,
well, sorry, you're not just acting on time, right? You are doing some internal thing as well.
Yeah. No, we're going to flip R. I'm going to flip theta also.
And also, you said it wasn't time. You said it was unstable ultimately. So
it is unstable ultimately. Let me come back to that. So suppose we go ahead and do this, and then I'm going to say that in the Schwarzschild coordinates, the phi form has the same solution in the left and right wedges, but both the dr and the dt are flipped, keeping the orientation of the electric part of the phi form. So then what we're going to do is, well, if I go to the right throat in these coordinates, the r and the theta are flipped relative to the left throat, so that although the solution looks the same. And so because of this, the orientation of the electric and magnetic phi forms look reversed. So what you do is you glue the right wedge and the right throat with an inversion of the gluing surface in both the theta and the r and some transverse coordinate, xi. And then you can check that that gives you a smooth geometry everywhere. So these inversions then are like inverting t, inverting p, and a flip of theta is a little bit, flip some r charges, so it's associated with the action of c. So it's like gluing an IR factor back into the UV with an action of the CPT. So that's what's going on in the solution. Okay, we'll come back to the T in a minute. But just to keep going, there is an instability. So if you consider a brain probe of this geometry, so we're gonna analyze the instability by imagining that we peeled one brain from one of the throats off, and we ask how long it takes for that brain to fall into the other throat. So you start the brain probe halfway between the two throats, and then heat up the geometry slightly, and you can work out what the action is. And you get some differential equation for the motion of the thing, and it goes like 1 over, there's an epsilon to the 6th that appears in the motion of the brain. So you can parametrically control the instability by making the non-extremality or the temperature small compared to the brain separation or the Higgs scale.
So I really can't resist, and I apologize in advance for this comment, but you're basically saying that one side can get sick and kind of throw up one of its brains if it has a high temperature, so it has a fever, and then it can infect the other one.
That's an appropriate metaphor for the time. Okay. Yeah. Yes. Fair enough.
I mean, we used to call this Fermi seasickness, is all.
I see. Well, Fermi seasickness then. Okay, so you get this epsilon to the 6th. So the next thing to study is whether or not you can make these things traversable. I see I'm running out of time, so let me. I'm going to run through the traversability anyway. So our two throats are separated by causal horizons, and so are non-traversable. But if the throat is marginally traversable, and you can introduce an ANEC violation, an average null energy condition violation, then you can make it traversable following the Gauss-Jafferis wall kind of reasoning. So we need to check whether along the v=0 Kruskal coordinate of the interior black-brane solution, the null component of the stress tensor satisfies TUU = 0. And if so, if you introduce any negative energy, you'll wind up having the integrated TUU less than 0, which will lead to traversability. So you can do a calculation in the fully spiced solution and show that up to some order in the brane separation scales, up to 1 over lambda to the 5th, it turns out that the time component of the stress tensor vanishes. So if you can introduce a null energy violation, you will be able to get through. So the further comment to make there is that to get such a violation, you can notice that after you Higgs the SU2n theory to SUn cross SUn, the Wilsonian RG flow is known to generate double trace operators of this form. So this is a trace f squared in the first UN times a trace f squared in the second UN, where I and J are the infrared factors of these two, of the original gauge group. So each of these single trace terms will be more or less dual to the infrared dilatones in the two throats. Because, if you had trace f squared in the full theory, that's dual to the dilaton in the complete solution. So because it's dual to the dilaton in the complete solution, these things are going to be dilaton in the infrared parts within the throats. So these double trace terms are of the right form necessary to generate this ANEC violation following Gauss-Jafferis wall, but only if they have the correct sign. It should also be said that other operators can be generated that are partners of this by doing supersymmetry transformations. So what we don't know is what the signs of these RG generated operators are, and the net effect that the sort of set of all these operators that you'll generate has in the stress tensor. And that would be interesting to understand. One could also add these kinds of operators or other kinds of relevant operators by hand, like one does in the Gauss-Jafferis wall protocol, but that's sort of less elegant. And it would be nicer if you could sort of generate these terms automatically from the RG flow. But I don't know if that's the case, but it'd be interesting to understand. So let me say one more thing before I end in view of the time. So suppose you started with 2 copies, A and B, of n = 4 Yang-Mills, and then you Higgsed each copy to get low energy factors, one labeled L and one labeled R. Then you have a low energy Hilbert space which contains 4 factors. That's this factor here, this factor here, this factor here, this factor here, corresponding to these 4 throats. So then if you constructed the product of 2 approximate low temperature thermofield double states, one relating these 2 and one relating these 2, then this state, you would say, using usual AdS-CFTology, would be a double wormhole between the between the A and B factors, right? You have the left and the right and the left and the right, and you entangle one left with one right and one left with one right, that kind of thing. So that's this solution. And for this solution, it's easy to splice. It's exactly the solution we had before. You just spread it out to the other side, and you allow it to go to 2 different asymptotic regions, so you don't have to worry about the funny splicing that we were trying to do. So I'm going to end there again in view of the time. And so what we claimed here was that there is a natural infrared entangled state in Higgsed SUn Yang-Mills theory that predicts that there will be an unstable solution for a large wormhole between 2 regions of a single AdS universe. We found this wormhole, at least in perturbation theory. It has an interesting interior topology with some sort of twisted gluing of the wormhole to the 2-center asymptotic spacetime. And 2 questions that you might ask is, because of this, because you've got to twist the sphere when you glue it back in, something interesting is happening with the sphere as you go around. There's a monodromy. And you could probe that by sending probes like spherical, basically R-charge probes, things like giant gravitons or spherical D3 branes through the wormhole. And it'd be interesting to understand how that works. Another interesting question is, can the RG flow in the Higgs theory naturally generate these infrared operators with the correct signs for traversability? So those are two things that would be nice to understand for the future. So I'm going to stop there. I think I'm pretty much exactly on time.
Thanks a lot, Vijay. Maybe we can all unmute and applaud Vijay for his nice talk. Great. So are there any further questions for Vijay?
Just a remedial question. You want to do this in some kind of flat splicing, like toroidal or planar slicing?
Yes.
Okay. Thank you.
Can I ask a question?
Actually, Douglas, I'm going to have to get back to you on the time flip or lack of time flip. So I will try to do that. I need to sort out something in my head about that, and I will try to get back to you later.
Okay. Okay. Thanks.
Yeah,
I
go
think
ahead.
Mehta also had a question. Is that right?
Yes. So I wanted to ask, do you have, it's not directly about this setup, but if I wanted to consider a dual for the magnetically charged black or wormholes that were recently discussed by Juan and collaborators, do you see how could they be embedded in the boundary theory, or some scenario that could correspond to that construction in the bulk?
So can you remind me of the details of these wormholes?
I think maybe the qualitative difference to me seems that you don't need the flux to go all the way to infinity. You actually have two black holes with opposite charges. Like, therefore, you will have a simple wormhole without any twist between them.
Yeah, so in that case, you're just running a flux through the entire wormhole like that and using the pressure of that flux to keep the thing up. So that's fine too. You could do that. The idea of this construction was that if you proceeded to do this thing where you Higgs the angles theory and you entangle things, it should have a wormhole. And the wormhole should have these kinds of flux properties. So you should be able to find it. That was the idea of the thing. So I think maybe you're asking, suppose you made a wormhole which had a magnetic flux running through the interior, what would the dual of that be? Is that what you're saying?
Yes, exactly. I mean, it seems that your construction was kind of motivated by the fact that you have the dual story, yes. A simple story in the field theory side. Yes. That other construction seems to be maybe a bit simpler in the bulk, but I don't have any I don't have any idea about how the dual would look like. I'm wondering.
So you're asking what is the state in the field theory that would correspond to having a sort of localized flux tube, if you like, running through this thing. So that I'd have to think a little bit about. Let's see. I'd have to think a little bit about that. They probably commented on that, right, in their paper. Maybe they didn't.
I don't know, but thank you.
Is the solution static or approximately static?
It's unstable in the end, right? So it's quasi-static, as in up to some order in the perturbation parameter, it moves slowly, or it doesn't move up to some order, but the differential equation tells you that at some order in the perturbation theory, this will start to move towards each other.
I feel like that's not what we would. So if we go back to the beginning of your talk about the entangling the two with the thermofield double.
Yeah.
That pattern of entanglement is not static. So if you evolve both systems forwards in time, then they locally decorrelate from each other. So the normal description of that is that in the two-sided black hole, as you evolve forwards in time, the wormhole gets longer. And, I feel like.
But if this is supposed to be a description, within each of these separate systems, this thing is going to look like it's thermal. So there'll be a potential for the scalar, so they'll fall together, right? So what's going to happen eventually with this is that this thermal, I mean, the Higgs value will go to 0.
I was thinking about, let's study it in the approximation where we forget about the potential. So we don't have that slow instability. We just have the, we neglect that.
Yeah.
Then from this picture, I feel like there should be on a rapid time scale, like that doesn't have to do with the branes moving together or not, like on a rapid order thermal time scale, the two systems should decorrelate with each other locally. So that the distance across the wormhole should get larger on a rapid time scale.
So that's certainly not what the solution does, but on this side, on the field theory side, I don't quite see why that should be the case.
Well, it's just because that's what happens in the thermofield double state. So that type of correlation disappears when you evolve forwards in time. It's like a very special state that has this delicate entanglement, and as you evolve forwards, it disappears. This concern is related to, this is trying to make a physical argument for the thing that Jinbin raised earlier, the concern about gluing the geometries together with the time reflection.
Yeah, so what if what you do is you, in the field theory, when you construct the state, you take the complex conjugate, I mean the CPT of the state in the thermofield double.
Well, I think that is actually how the thermofield double is.
Right, and so that's like doing the reversal, right?
No, but they still, if you evolve forwards, they decorrelate. Like there's a direction of time that you get from, so the Hamiltonian is bounded from below.
Yeah.
So that tells you which direction Euclidean time should go.
Yeah.
And then there's if you know which direction Euclidean time, which direction corresponds to positive Euclidean time, you know which direction corresponds to positive Lorentzian time. And if you evolve in positive Lorentzian time on the two sides, then they decorrelate.
So what would that mean for this state? You would say that this state as constructed here, in this picture over here, as you ran time up in the Yang-Mills theory, this state would decorrelate.
Yeah, that pattern of entanglement would disappear. So that the bulk description of that state should be highly time dependent.
On a fast time scale.
Yeah, in the same way that a two-sided black hole is highly time dependent.
Now, if I think about the Hamiltonian in each of the low energy SUN factors for the moment, right? So suppose I didn't think about the UV part of the thing and talk about the low energy part of it. And the low energy part of it, then if it is like the thermofield double, then if I ran the time in the opposite directions of the two low energy things, then that would be like the stable correlation in the thermofield double state. Is that right?
Yes, but that's not that time direction isn't a physical time direction. Like
no, I understand. That sounds like what this T to minus T thing in the splicing in the IR was all about. That IR time that was being
suspicious of that.
Yeah. Okay, so that's a useful point. And I don't think I'm going to be able to answer that on the fly here. And we'll have to think about it.
Okay.
And I will. And we'll get back.
I do have a different question also.
Sure.
For the question about traversability.
Yeah. Should I move forward to that slide or so?
Okay. Well, I was just wondering, even in the what is it that determines how far apart so you talked about the two paths through the one that had the Klingon ships and one that didn't?
Yes.
Is there something that makes the path with the Klingon ships necessarily shorter than the other one in your setup?
I don't know, but there must be.
Okay.
Because it's got to be the case that the path through the wormhole is longer. I think we even tried to check that at some point and had some reason why it was longer, but I don't know what the general sort of principle here is that makes that true. But that's got to be the case, otherwise you'd have some issues.
Okay, I see. Okay, thank you.
Yeah, let me think about the time and the flipping and the IR running the time in the opposite direction. I thought that the IR time flipping in the running the time backward, the thermofield double on the two sides to maintain the correlation, I thought was the reason why it was natural to do the splicing in the opposite direction at the edges of the throat. But I take your point that if you run it as a global time the same way throughout, then you would expect a decorrelation. I take your point there. So let me think about that a little further, because in so many ways the solution does seem to reflect all the things that you'd want from this from the construction, except for this point that you're raising right now. So I think that has something to do with the sort of various flips of orientation and the times and things like that. Let me get back to you on that. I will think about that in the next day or so.
Any other questions for Vijay?
Sorry, can I just make sure I understand the remedial point? In the case of the thermofield double, the flux is just going straight through, right? Yes, so that's as if it's a brain and an anti-brain throat or something.
Yeah.
Yeah, okay.
And so the fun and games that we had to play in order to get this thing to splice back to the same universe was that if you take things that went through in this way, I don't know if you can see my hands, but if you
I can.
And then you sort of bend it and point it back, it goes in one place and comes out the other. But you kind of want it to come out. You want the flux to come out in both directions.
Right. So it is different from the thermofield double in the Subtlety theory.
It is different from the thermofield double after you've spliced it together. So I take the question that was asked by Douglas, and I forgot who else asked me the question. I'm sorry. Involves two things. The two parts of that question involved, if you were doing the standard thermofield double and you ran time globally up on both directions, then the state would appear to decorrelate pretty quickly.
Well, right. That's just the singularity forming, right? I mean, that's okay. That's but that doesn't. Yeah. But you from the beginning you knew it wasn't exactly that solution in 10 dimensions.
It is that solution in 10 dimensions.
It's not that solution.
It's not that solution in 10 dimensions. So, and I think what we're trying to go after is if we run the thing in the opposite direction, then the thing looks stable. But I think Douglas's point is that if you construct the thermofield double state, and in the way that I had written it down and ran time up, he's saying that state would decorrelate pretty quickly. So I should be able to see that in the solution too. That is to say,
sorry, you're not doing the thermofield double state. You're doing something else with the internal degrees of freedom.
Yes.
Right. So it's a somewhat differently entangled state than that one.
It is.
But I'm not answering the question. I'm just trying to understand what the cases are.
No, absolutely. So it's somewhat differently entangled from that, and particularly UV properties are different because it's been sort of cut off in some way. That's one thing. The other thing is a thing that I'm still sort of not completely coming to grips is that running time forward in both directions of the throat. I think what Douglas is saying is not inconsistent with what we're doing, but I'm having trouble articulating why. Because we're running the time in opposite directions on the interior and then splicing it to the outside. But then we could have run time. I mean, that's just a choice, right? You can choose to run time this way also. And then I think you would get, you'd approach the singularity. And if you approach the singularity, something else would happen. So I need to sort out a couple of details there. But it's not.
Thanks a lot. I mean, it seems to me this is interesting either way it goes. Like if there ends up being some faster instability. Well, okay. Anyway, if there were any problem with the solution, if there was some no-go theorem for the solution, then the kind of meme that entanglement is space-time knitting together would be, you'd have a counterexample to that, and that would be interesting in itself, right? So
Yeah, no. So
I think
I think whichever way things go, it's interesting. And in any case, by the way, the solution, if you don't try to splice it back into the same space, there's a double wormhole that you can construct for it for free, because it's just you run the solution in both directions. So that you can do for sure. But really, the question is, is there an additional instability here at a faster timescale that should be somehow happening? We couldn't spot one. It looked like it was.
So let me just ask it one more way, which is, were you even counting the standard shrinking of the sphere inside the black hole, which is the instability that I think Douglas is talking about, as one of your instabilities?
No.
So it might be there. I mean.
Oh, I see. Yeah, no, the thing that we were talking about here was, if you look at the outside, if you look outside this object, then the two throats are separated by some distance.
Yeah, I understand that instability. Yeah,
yeah,
but it's different.
That's the instability we're talking about.
Yeah, but to the extent that you were thinking it was basically splicing in the standard black hole geometry with a twist internally, that standard black hole geometry has in it the singularity.
It does.
I think what's the instability I was worrying about is when you're running twist the time variable, you consider about matter field. Then with respect to that time killing vector, the matter field won't, the Hamiltonian of the matter field won't bound it from below.
So Zhenbin, you're not talking about the stretching inside and the singularity inside per se. You're talking about extra.
Yeah, that's why in like the two-sided black hole, we do not consider about time like going forwards and backwards on the two sides. We're always talking about time going upwards. That is a stable theory even for the matter field on this geometry.
Well, I think you and Douglas are sort of talking about two opposite things. One is it's going to be singular within a light crossing time, even in the geometry, and then you're saying something else about the matter. Is that right? I mean,
well, yeah, I think Douglas saying is like argument like if this is if this geometry represents a thermofield double state, then this geometry cannot be static, and in particular, you will see correlation decays as a time goes on.
But that in itself is just the black hole, the usual black hole interior, correct? Or?
Yeah. That's right.
But that's going to be the case here too, right? If you take we're looking at some equal time slice here, and if you keep going up, in the Penrose diagram, there's eventually this thing is going to shrink on the interior. That's for sure. So that's not the statement made here about the slow time scale of the instability. It's a question of, if you look from the outside, how long does it take for the two throats to come towards each other? That's a separate question. Right? You can have throats on the outside be far apart and the inside be collapsing. That's a separate question about what's happening on the inside.
So it sounds like Zhenbin is asking a third question.
Yeah.
Yes.
I think they might be related, because if the boundary time corresponds to going up in one direction, down in the other direction, then the size of the slice remains constant. That's how I think it's related to Douglas's point.
So that's a question about Vijay's solution, is whether or not, I think people might be getting confused by the words. I mean, I am, but so if Vijay is telling us that the solution has the property that it's shrinking, I mean, I see what you're saying, that they're related, Meridad, but if it's the case that Vijay's solution actually shrinks and goes to the usual black hole singularity with the extra dimensions doing some twisted thing along the way, then that would at least answer that version of the question. So there's no rush, but it seems like you were saying that.
Yes. So the geometry inside the wormhole part of the thing is the standard black-brane geometry. So you can slice and dice that in any way you want. So if you draw it, if you were to take slices like this, then what's going to happen is, over time it's going to shrink, because that's what has to happen in the wormhole geometry. So it's a question of, are you going to look at it like this along slices where the time tilts like this, or are you going to look at it along slices that go like that? So that's
okay.
right? I think that's so. If you look at it like this, then you're not looking at slices that shrink. But if you look at it cutting across like this, then it certainly looks like you've got shrinking slices.
And which one are you doing when you evolve? I mean, that.
I mean, we're not evolving the interior per se, right? I mean, so what we're doing is we splice the solution, and then what we try to say is that if you look at the outside, so the solution looks in along some equal time slice. You then take that as an initial condition, and then you try to evolve that forward in time. And we're trying to say that you look at that solution in these kind of coordinates where this time is going up this way like that, tilting like that. The solution looks quasi-static. But as time passes, eventually the two exterior throats are going to start coming closer towards each other. So the whole thing is going to collapse in that way. So I think the confusion here has something to do with whether this, looking at it in those coordinates in some way is going to lead to, if I try to quantize the matter fields on this global background, am I going to have some issue with boundedness of the Hamiltonian? Is I think really the question that's being that we're going after. There's also, as you said, I think there's two or three different points. There's another point involving slicing like this, and these slices are supposed to get smaller. So if they're getting smaller in this construction, where do those slices live as you go up? So those slices getting smaller has something to do with this decorrelation that Douglas was talking about. So I need to sort out these three different potential questions that are there. One is the quantization of fields on these slices, given that you have stuck thing together. Then there's the issue of where do these slices go, right? So if you make slices like this, what do they look like when you try to transport these back to what you're going to interpret this as in the field theory? So that I think there's a couple of questions of that kind. And that goes to the point of okay. So there's this object in the field theory that looks a particular way. I don't think there's any question that you can make it. Then there's the question of, I believe that this thing here is a solution, at least to the gravitational equation of motion. So the question is, what is their relationship? And
is there any thing about the fermions in this kind of parity inverted situation? Is it's consistent with the fermions of
the whole thing as constructed, the whole thing is orientable.
Okay.
We've done enough flips so that the whole thing's orientable. So I don't think there's an issue because of that with fermions. Otherwise, there'd be an issue with fermions. So because there's a flip on the theta and there's a flip on the p, on the x sides. So at the end of the day, it's orientable. So that's a good question. So
now I think I appreciate all the questions better anyway.
Yeah. Okay, I'll sort of that, and I will drop you a line.
All right. So if there are no further, I should ask: are there any other quick questions that anybody wants to ask Vijay? Okay. So if no further questions, let's thank Vijay again for his beautiful talk.
And thanks a lot and thanks for the invitation, and thanks for all the wonderful questions.
Yeah, thanks a lot, Vijay. It was a nice talk. We enjoyed it. Thanks a lot.
Okay, talk to you soon.
Bye-bye. See you all.
Bye-bye.